Okay, Tom, it's lovely to have you here, and which is another episode of Talking in the Library. Today we're going to be talking about physics, and I wondered first, what would you think the biggest challenges in physics are at the moment?
Well, I think the biggest challenge for the last almost 50, 100 years is we've got two big camps. You've got quantum mechanics and you've got general relativity, both that have been extensively proven. So a few years ago we had the gravitational waves discovery, which Einstein postulated 100 years beforehand. So his theory clearly works, and quantum mechanics is famously the most tested theory ever because it doesn't really make a lot of sense on paper and you have to test it, test it, test it. So both work, but they don't allow for each other to work. So there is sort of an area of overlap that's missing. And I think the biggest sort of challenge in physics, taking away some of the more social issues of climate change and that sort of thing, is definitely trying to sort of reconcile these two theories together. And if we can manage that, then we've got a very good understanding of how things work.
That's very interesting. Now, just for the layman, could you explain how you test these theories there?
Well, it depends on sort of what they say. So a lot of the causality of what they say you can observe. So in general relativity, Einstein said that space is like a bed sheet, if you will, of space and time, and putting bits of mass on it creates dimples, if you will. And the more mass those objects have, the bigger the dimple, and this is what we perceive gravity to be. And when we've got two massive stars, the neutron stars, coming together and they collide, basically get concentric rings forming, and these form gravitational waves. This is what one of the things that Einstein came up with when he was thinking about this. And then we tested this, well, I didn't personally, but so in America and I believe in Italy, they had mile-long lasers, and what you'd expect when gravitational waves come together is a very slight distortion of space-time, which means that you'll be able to tell when a wave hits due to the laser, because in itself it basically contracts. It does some weird things, and that way you can measure it. So it's things like that. And with quantum mechanics, so the way it first came about is the photoelectric effect. So this is why warm things glow red and things like that. So the way we tested it is you fire a high frequency light wave at a piece of metal. So let's say aluminium, and we're firing something in the ultraviolet and above range, and you'd expect electrons to come off it. And you can easily detect these through photographic plates or even just a simple ammeter, and that's another way of testing that theory.
Oh, that's very, very interesting. So obviously there are a lot of scientists that have influenced you, but who do you think is the most influential scientist of them all?
Well, obviously, the last 100 years in itself, there are so many great people that have worked on so many great things. So the likes of Einstein, Bohr, you've got Pauli, Schrödinger, all these great sort of physicists who came up with some great things. James Clerk Maxwell, Chadwick, all these great people. But for me, where I think it all started would probably have to be at Newton's level, I would personally say. Because he managed to bring together mathematics and physics in the elegant way of calculus. Yes, of course, Leibniz was doing it at the same time independently, but just the way he came together and his knowledge of the subject. So there's a famous story of I believe Swiss mathematician, one of the Bernoulli brothers. So there's about three of them who were very good mathematicians, known for lots of different things from fluid mechanics up through to mathematics. And one of them set a challenge to every single great mathematician at the time that is called the baristochrone problem, which is the fastest point from getting to A and B and the path the particle would take to get from those points. And he sent it out to all these people, and it took them quite a long time to solve it. And the legend has it that it once got to Newton, and within a night he solved it and sent it off to Bernoulli, and didn't even put his name on it because he thought it was so trivial and so easy. They didn't even want it sort of associated with him, and after they worked it out that it was clearly him. I think he said it, I know a lion by his claw marks. And it's that sort of idea that he managed to bring so much together, and his theory is, okay, might not be 100% correct now, but this is 400 years ago, and we're still using laws of motion, we're still using laws of gravitation and all these great ideas for engineering and physics that it just surprises me how well he got it for the time, and especially with the advent of calculus in itself. I don't think anyone could be doing any sort of science or maths or anything without that. So I'd have to say Newton.
That's very, very interesting. So some of your blogs have been centered around quantum mechanics. How important do you think it is for the average person to understand quantum mechanics and indeed physics, physical theory, physics generally?
Well, with quantum mechanics, I don't think anyone truly understands it. I think famously, whenever you read a book on it, it probably start along the lines of, if you think you understand it, you have no idea what's going on. And it doesn't make sense. It's about how things that are made of matter can suddenly be a statistical wave, and how things can be detected in two places at once, and tunneling and transportation, all this is really odd stuff. But I do think it's quite important that everyone has.
Keep going.
Everyone has an understanding of the physical processes, because otherwise you don't really appreciate all the work that's gone on. So with quantum mechanics, for example, obviously a lot of work went on, and a lot of what's been brought about through it influence our whole lives. So lasers, for example, quite an easy thing. We've all used them, and we wouldn't be able to use a disk drive, for example, without them. That's all down to quantum effects. And I don't think that everyone should know exactly how it works, but just be able to appreciate the effort that went in, and that there is a lot more to technology and more to everything that meets the eye. I think the more you know about it, the more you appreciate it. I think it just makes things, I think, quite a lot more elegant. Things out. But physics in general, I think it's important that everyone has a basic understanding of how the world works. We get very much tied up sometimes in our own beliefs, but physics is universal, and just being able to say, oh, okay, why does the Earth orbit the Sun, for example, or how do computers work, or why does my hair stick up when I rub a balloon against it, things like that. Just being able to understand those little sort of tricks in life and quirks, I think it's quite interesting. I encourage people to find out more.
No, it's very interesting. I'm just going on a slight tangent here. You talk about beauty, and quite often, if we talk about beauty on the curriculum, it will be art, it will be poetry or prose as looking beautiful. Why do you think science and physics is beautiful? Because for humanities students and teachers, they don't often associate with beauty.
Well, this is sort of actually one of the reasons when I was thinking about what degree I was going to do, and I wanted to do physics, but I couldn't not do maths. I had to keep on doing it, so I ended up deciding I want to do physics and a maths degree. But maths in itself is a universal language, and it is very elegant. So just simple proofs can really show quite a lot, and it all just sort of makes logical sense. Whenever you're doing a maths problem and you've worked a bit hard and you've gone down a load of dead ends and whatever, and you finally get to that point, not only is it satisfying, but to see the logical jumps and that clever trick there, I think it just makes more sense to me and sums up more about with what I suppose in essence humanity is about, finding out stuff. We like to find out things, and yes, of course, art and poetry in their respective rights can be beautiful and artistic, but just being able to work from a very simple postulate to a rigorous mathematical proof and hence a physical proof, it's just really satisfying. So especially one I always like to do is proving, is looking at, say, a roller coaster, getting rid of friction aside, how it's actually independent, how fast you go around. No, sorry, the loop, if you have it connected to it, is independent of the mass of the roller coaster, for example. And that's just quite, you wouldn't think about it, but once you prove it, it's quite elegant. So I had to prove recently, on another note, is flying from London to New York and back, and the effects of a wind in both directions. So it's a constant wind, either flowing so one way against you and one way with you. It doesn't really make any sense, but it doesn't matter which way. If there's a wind on one direction, it will always slow you down, even if it then helps you in the other way.
See.
and you can prove that mathematically quite simply, but it doesn't really make sense. But seeing the proof done of that, I thought it was quite clever and just quite cool, really.
So essentially, if you understand maths, you understand physics.
Yeah.
The reality that many people just take for granted, you can explain exactly why things are the way they are.
You can have a good approximation. Yeah, I think that's just quite cool.
That is beautiful, isn't it? Now, finally, what do you think are the most interesting areas of physics that you've looked into as in your time studying?
Well, I suppose quite basically, laws of motion are always quite cool, and fields, gravitational, electric fields, magnetic fields, are quite cool to look at. But outside of the curriculum, because I think the physics A level curriculum is quite restrictive in some senses, and it's not very rigorous. I very much enjoyed looking at quantum mechanics and the wave function. So I read a book by Jim Al-Khalili, talking about quantum mechanics, and there's this issue called the wave function. It's basically saying, very simply, you don't know, due to the uncertainty principle, you don't know where an electron precisely is and the energy or its momentum at that point. You have a guess, and it's due to a statistical wave. And he explained it very nicely using an analogy of a crime wave. For example, if a criminal robbed this room right now, the police would know exactly where he is at this moment in time. But as soon as time goes on, we don't know exactly where he is. We could go to Southwoods, for example. He knows there's a load of computers over there. So he could be, there's higher probability he's over there, but we don't exactly know where he is, and it then collapses himself. There's that sort of thinking that doesn't make sense, that an electron can be in many places at once until it's observed, and by observing it, you are influencing it. Quite cool, quite interesting. But then look outside of quantum mechanics, obviously relativity is always quite cool to look at. But for me, thermodynamics actually, because it isn't covered a lot in the physics course, which I think is quite wrong. And I looked at the first, second, third, zeroth laws of thermodynamics and things called Carnot engines, which basically prove that you can never have an engine that's 100% efficient. And even if it gets close to that, the actual usefulness of it is nothing. It's just all these sort of unconnected areas of physics coming together, thinking, oh, okay, that's why that happens as it does, or that makes sense, or oh, I get now how a laser works, or oh, okay, that's why the planets behave as they do. I just think it's quite interesting, and the more you sort of learn and uncover, the more you can explain things, and I just think that's quite cool.
It is cool. Just one last question. Obviously, you've studied a lot and you've read around. Are there any areas of physics that you're looking forward to study that you've not studied yet?
I do want to. So, A level wise, you look very much at relativity quite superficially. When you read about it, you look at it quite superficially because you have to understand a lot of maths to do it. Same with quantum mechanics. So I sort of understand the phenomena, but I couldn't describe mathematically, for example. So I'm really looking forward to being able to manipulate these equations at a higher level and showing why. Thermodynamics looking forward to, but just I think something that's and fluid dynamics I think quite interesting as well. But it's just personally I really like the areas of mathematical and physical overlap, those sort of niche ideas, using maths to solve physics, for example, the other way around. So that barista-chrome problem I spoke about earlier, one of the competitors, one of the Bernoulli brothers himself, looked at it not in terms of a particle, but light moving from A to B. Yeah. And because light obviously will take the fastest path, then he used a physical idea to describe a mechanical problem. And I think that was just quite a cool link. And it's those sort of overlaps that I'm really looking forward to sort of just getting stuck into, really.
Okay, well, I'm sure you'll enjoy your study of physics at university. And thank you very much, Tom. Very interesting.